praise our lords, God, Timquatu, and the Son of God have reunited. The three most powerful are one.
Welcome to our show, Interstellar Tunnels, Hidden Pathways in Our Galactic Home, Part 1 of 2. Displaying the glory of creation, our magnificent universe is filled with wonders. Some lie far beyond our comprehension, others we cannot even imagine exist. And yet, with each advance in space technology, the cosmos reveals itself anew. Knowledge about our place in the universe is gently and sometimes dramatically overturned for the better. Guided by ever more sensitive instruments, scientists are now discovering events and structures that remained invisible only decades ago, findings so unexpected that they continue to astonish even the most seasoned scientists. Still imagine our solar system as an island of planets floating in vast space? Scientists have revealed the opposite. We now have a hot, eventful, and extraordinary cosmic neighborhood. Science confirms that the Sun is embedded within an enigmatic but structured cavity in the Milky Way. Shaped somewhat like a peanut or an hourglass, it has a charming name, the local hot bubble.
Did you know that Earth and our whole solar system are inside this weird bubble in space? For real, our galaxy is normally crowded with dense clouds of gas and dust. What you're seeing here is based on real data from the Gaia Space Telescope. But here's Earth, and around us is this pocket of relative emptiness. The blue here shows its edges. We call it our local bubble. We think it was created by shockwaves from supernova explosions pushing other stuff away. And our solar system only moved into it about 5 million years ago, when early human ancestors were alive. We'll keep on going through it for another 10 to 20 million years, but it's lucky that we're in it because that bubble allows us to see around us more clearly.
The local bubble was created by powerful shockwaves from a series of supernova explosions that began more than 12 million years ago. When these supernovae exploded, they forcefully pushed interstellar gas outward like a popcorn.
And what is remarkable, our sun is practically in the center of this bubble. Scientists at the Harvard-Smithsonian Center for Astrophysics, CFA, proved that yes, we really are in a kind of void. They conducted the most complex computer simulations, creating a three-dimensional reconstruction of space and time. The study showed that the Sun and Earth are located almost in the center of a giant bubble with a diameter of 1,000 light-years, which they called the local bubble. According to calculations, it began to form about 14 million years ago. For this, it's necessary that about 15 supernovae explode over several million years. This series of explosions pushed the interstellar gas outward with the pressure of light, creating a bubble-like structure with a dense surface at the boundary. And now, the bubble continues to grow in size. When the bubble first formed, it was expanding at about 60 miles per second, according to data collected by the European Space Agency's Gaia Space Observatory. At present, the bubble is still expanding at 4 miles per second.
Imagine this, 15 ancient supernovae erupting close together, all within a short span of cosmic time. How splendid the sky must have been! How did scientists discover the local hot bubble? Well, the journey takes about 50 years. The idea of the local hot bubble first emerged in the 1970s when astronomers detected a faint all-sky glow of soft X-rays, radiation consistent with million-degree low-density plasma filling nearby space. The bubble was proposed as a possible source. Doubts followed in the 1990s when scientists discovered that X-rays could also form through interactions between neutral atoms and the solar wind. But in 2014, NASA observations confirmed the existence of the local bubble, identifying about 60% of the X-ray glow as coming from interstellar plasma surrounding our solar system. Supernovae also left several radioactive isotopes on Earth.
Evidence of these ancient explosions has been preserved in our Earth's geological record in deep-sea sediment deposits in the form of a special isotope called iron-60. This radioactive isotope can come from a few different sources, but the most common source of iron-60 is believed to be supernova explosions. We know that the source of the isotope is extraterrestrial because the Earth itself has no way of producing iron-60 on its own. It decays into cobalt-60, another radioactive isotope, before it finally decays into nickel-60, a stable element. Iron-60 has a half-life of 2.6 million years, and cobalt-60 has a fairly short half-life of just 5.3 years. Because of this, when we find a deposit that contains these elements, scientists can compare the amounts of iron-60, cobalt-60, and nickel-60, like an elemental clock, to reveal when that material was deposited on our planet.
If the local bubble's thin, fiery interior is intriguing, its compressed, dense surface is even more remarkable. This vast boundary is where cosmic endings became beginnings, where dying supernovae compressed gas and dust, giving rise to new generations of stars. In 2019, astronomers took a major step forward. Using data from the European Space Agency's Gaia Observatory, scientists assembled the first three-dimensional map of the local bubble, revealing its shape in unprecedented detail. Then, in 2022, a study published in Nature went even further. Researchers modeled how the bubble expanded over millions of years and identified nearby star-forming regions along its surface. For the first time, astronomers revealed that many nearby young stars were born in the star-forming regions near us, the surface of the local bubble surrounding the Sun and the planets that orbit it. Supernova shockwaves swept up interstellar gas and dust, compressing them into cold, dense molecular clouds, stellar nurseries on the shell of the bubble. There, gravity takes over. Gas and dust begin to collapse inward, spinning and heating as they condense, until a glowing protostar forms and eventually ignites nuclear fusion to become a true star.
Supernovas are one of the brightest and most energetic explosions in the universe. A Type 1 supernova occurs in binary star systems in which one of the stars is a white dwarf. The other star could be a red giant, a main sequence star like the Sun, or even a white dwarf. In such a binary system, the white dwarf begins to gravitationally attract the gas from the atmosphere of the red giant towards itself. Most of this sucked up gas is hydrogen. When it reaches the surface of the incredibly hot white dwarf, it rapidly ignites, thereby creating an explosion, or Type 1 supernova on the star's surface. In contrast, a Type 2 supernova results from the death of a single massive star. When a star can no longer continue nuclear fusion in its core, it starts collapsing under its gravity. As a result, the star's outer layers collapse inwards in a fraction of a second with about 23% of the speed of light. Since the neutron degeneracy pressure halts the collapse of the core, the incoming outer layers rebound back after colliding with the core, causing shock waves, thereby detonating as a Type 2 supernova. In both cases, when the supernova expands outward, it strikes and compresses the material into which it expands. This results in the creation of dense knots of molecular gas floating in the interstellar medium. These dense regions further collapse under their gravity, thereby forming young stars.
Researchers were able to trace the motions of nearby young stars backward through time and bring to light the eventful past surrounding us. We have reconstructed the history of our galactic neighborhood, said the lead researcher, Dr. Katrin Zucker, a former NASA Hubble Fellow at the Space Telescope Science Institute. We already know that 15 supernovae once tore through this corner of the galaxy, carving out the local bubble. But the explosions did not simply clear space, they also set the stage for new creation. So how many stellar nurseries now trace the rim of the local bubble around us?
It's really at this edge of the bubble that we actually find some of the most active star-forming regions, including all of the regions you see right here.
On its surface, 7 star formation regions were detected, dense molecular clouds where stars are formed. The process of star formation occurs everywhere on the surface of the local bubble, and there are many such bubbles in the galaxy. Therefore, it's possible that there are other stars, even with planets, which, like us, are also in their local bubbles.
As the local bubble took shape 14 million years ago, our sun was still far away. Only about 5 million years ago did it drift into this vast cosmic cavity. Today, the sun sits near its center. It is expected to leave after another 10 to 20 million years. Aren't we fortunate to be so close to the birth of new stars today? What a precious God-given opportunity for Earth-dwelling humanity to observe and learn from the never-ending vibrance of our magnificent cosmos, right here in our own galactic neighborhood. As humble specks in the universe, we deeply admire and appreciate God Almighty's majestic plans for the stars and for humankind. Welcome to our show, Interstellar Tunnels, Hidden Pathways in Our Galactic Home, Part 2 of 2. The vibrance of our universe is a timeless song, with stars dancing between presence and absence. When massive stars reach the end of their lives, they do not fade quietly, they explode. Each supernova sends powerful shockwaves racing through space, blasting hot gas outward and carving vast cavities in the interstellar medium. Over millions of years, enormous bubbles of hot, low-density plasma inflate and scatter throughout galaxies. Astronomers now understand that this process has profoundly shaped the Milky Way. Rather than a smooth ocean of gas, our galaxy is riddled with hollows, tunnels, and local hot bubbles, more like a gigantic cosmic sponge. In 2023, a research team from the University of Virginia and the Center for Astrophysics, Harvard and Smithsonian, or CFA, analyzed magnetic field data from the European Space Agency's Planck Observatory. Their three-dimensional magnetic reconstruction revealed with striking clarity the structure of the local hot bubble, or LHB, surrounding our solar system.
Research author and astronomer of CFA, Elisa Goodman, explains in her statement that, statistically, the sun would not be near the middle of a huge bubble if they weren't spread all over the place. The local bubble is exactly the bubble we're in right now, she said. We think the sun has probably gone through a lot of superbubbles in its history.
What can the local bubble tell us about this celestial sponge? That question has driven a new wave of research. In 2024, scientists at the Max Planck Institute for Extraterrestrial Physics turned to data from eROSITA, the X-ray telescope developed by the institute and operating aboard the Russian-German Spectrum Röntgen Gamma, or SRG mission. eROSITA divides the sky into thousands of finely detailed segments, detecting faint X-ray signals from hot gas, cavities, and hidden interstellar structures while charting vast numbers of galaxies across the universe.
One major advantage of eROSITA is where it operates in space. Earth's atmosphere stretches surprisingly far, with a vast halo of hydrogen called the geocorona, extending up to 100 times Earth's radius, which is more than 370,000 miles from the surface. eROSITA is mounted on a space observatory stationed about 930,000 miles from Earth. At this gravitationally stable point, where the poles of Earth and the Sun balance, the X-ray observatory is uniquely positioned as the first to capture X-ray images of the sky, from completely beyond the reach of our planet's glowing geocorona.
Using eROSITA data, a research team at the Max Planck Institute for Extraterrestrial Physics refreshed observations of the local bubble. A temperature gradient within the local bubble was identified, revealing a north-south contrast at high galactic latitudes. The galactic south appears hotter than the galactic north, an asymmetry consistent with a supernova-driven origin. It suggests uneven heating or later stages of stellar explosions in this region of space. The team also discovered that the local bubble is expanding more towards the galactic poles, where the resistance is lower. Rather than spreading evenly along the plane of the Milky Way, the expansion moves more strongly away from the galactic disk. More importantly, by combining new eROSITA observations with earlier data from the Rosset All-Sky Survey, scientists were able to construct a far more precise three-dimensional map of the local bubble. It offers the clearest view yet of the cosmic structure surrounding our solar system. The colorful image of the local hot bubble we see here represents a cluster of overlapping cavity fragments left behind by supernovae explosions that occurred over millions of years.
In the new 3D map, our local hot bubble looks like a three-dimensional splatter surrounded by and even overlapping other galactic structures. These other structures represent known supernova remnants, like the Gum Nebula shown here in red, and dense molecular clouds, shown here in orange. With the new data and 3D maps, these superbubbles seem likely to be common in our galaxy. The cavities of our galaxy are blasted out by gigantic supernova explosions, with new stars forming along the edges of the holes created by dying stars. And it appears that some of these superbubbles may have tunnels connecting them to other bubbles or other structures, suggesting our local hot bubble could be part of an intricate network of similar features throughout our galaxy.
For decades, interstellar travel was imagined through theoretical space pathways that are visible only in science fiction. But scientists at the Max Planck Institute for Extraterrestrial Physics have revealed something far more tangible: interstellar tunnels linking the local bubble to distant regions of space. Unlike hypothetical wormholes, these tunnels are real, observable structures woven into our own galactic neighborhood.
Astronomers have uncovered a hidden interstellar tunnel, a cosmic highway connecting our solar system to distant stars. Imagine a vast, invisible web stretching across the galaxy, linking us to distant constellations in ways we never dreamed possible. Recent advancements in astronomy have allowed researchers to map this region with unprecedented detail. Among the most surprising findings are tunnels or channels of hot plasma stretching out from the LHB, appearing to connect our solar neighborhood to distant regions of the galaxy. Such features challenge the perception of the LHB as a homogeneous structure and suggest a history of multiple overlapping events, including recent supernova explosions that reheated parts of the bubble.
So, what are these tunnels made of? They are sculpted by two powerful forces. First, the explosive shockwaves of supernovae, and later, the steady push of stellar winds blowing from newborn stars.
These tunnels, composed of hot, low-density plasma, appear to act as conduits linking our solar system to distant star-forming regions and other galactic structures. These tunnels are part of a larger, interconnected network within the Milky Way, created by the cumulative effects of supernova explosions and stellar winds. Supernova shock waves carve cavities into the interstellar medium, while stellar winds from massive young stars further shape these tunnels, creating pathways for the movement of energy and matter. The discovery validates earlier theories about interconnected cavities within the interstellar medium. It reveals a dynamic galactic ecosystem where tunnels and cavities facilitate the transfer of materials like gas and dust.
So far, scientists have identified two interstellar tunnels within the local bubble.
We have the Canis Majoris Tunnel, which lies on the Milky Way's galactic disk, and is believed to connect our local hot bubble to the Gum Nebula or another larger nearby superbubble. But the 3D map also revealed another, previously unknown interstellar tunnel, stretching towards the constellation Centaurus, possibly connecting our local bubble to the neighboring Loop 1 superbubble.
The team suspects that the Centaurus tunnel in the LHB may just be a part of a network of hot gas tunnels, a larger, interconnected network of hot bubbles and cosmic tunnels that make up the galaxy, an idea first proposed in 1974 but lacked significant evidence until now.
Interstellar tunnels may not be comparable to the bridges for celestial travel that Dr. Albert Einstein, vegetarian, and physicist Nathan Rawson envisioned nearly a century ago, but they function as interstellar highways carrying vital cosmic material, including crucial components for young stars through the galaxy, between the interior of the local bubble and regions where new stars are born.
These findings underscore the complexity and interconnectedness of the Milky Way's structure. The tunnel's low-density nature makes them efficient pathways for the propagation of cosmic rays, high-energy particles originating from supernovas and other phenomena. This finding enhances our understanding of how energetic particles travel across the galaxy and their impact on astrophysical processes. Interstellar tunnels may also play a role in star formation by connecting distant star-forming regions and enabling the transfer of gas and dust. These materials, essential for star birth, can accumulate in specific regions along these pathways, triggering new stellar activity. This connection positions the tunnels as crucial components in the Milky Way's star formation cycle and enriches our understanding of how stars and planetary systems come into existence.
Though the galaxy may seem distant, our solar system, nestled within the local bubble, is part of a living network that carries the rise of new stars. Even from our small vantage point, we are woven into vast cosmic passages, participating in the galactic unfolding not only through scientific discovery, but also through the actualization of our better qualities as humans, through appreciation, care, and love for all beings. May our choices and actions contribute to these uplifting, creative pathways towards a noble cosmic future.
Animals feel pain, just as humans do. Animals express emotions and may love their offspring and those close to them, not so differently from the way we do. The Venerable Radhanath Swami, vegetarian. All glory and love to the three reunited most powerful God, Tim Kotu and the Son of God, for all your boundless grace.